Hi, welcome back. So today we will go into the second chapter of S2, which is on the Poisson distribution. So the Poisson distribution uh, is first, this is a discrete probability distribution. Previously, we learned one type of discrete probability distribution, which is the binomial distribution. So this is another type of discrete probability distribution. So it is used to model events that happen randomly in a given period of time or a given window. So usually we will write something like this. So X is distributed by the Poisson distribution, and it only depends on one parameter, which in this case I call it as lambda. So remember that a Poisson distribution depends on one parameter, which is written as lambda. So this lambda will be your mean, and it will also be your variance. Okay. So the probability for a certain event that happens will be written like this. So probably I rewrite this. So this is given by this particular formula, e to the power of minus lambda, and then you have lambda power r, and the whole thing is divided by r factorial. So this will be the probability for x equals to r event to occur, for example. So as you can see, this r can goes to infinity, but very unlikely. So there are a few things that you need to take note of, whether or not a particular event can be modeled by Poisson distribution. So the first one is that so perhaps I should write assumption. Sorry. To model with the Poisson distribution. There's no apostrophe s. So the first one is that the occurrence of one event does not affect the probability of a second event. The second assumption is that the average rate at which events occur is independent of any occurrences. And then the third thing is that two events cannot occur at the same time. So you combine these three together, basically you have independence on the second assumptions. First one is that it happens randomly. So you have random events. And then the last one is basically it cannot occur at the same time. So the keyword is singly. So let's look at one example of a Poisson distribution. Let's say you have a fire station. It receives some emergency calls. So if you look at this particular situation, you have an average number of certain event to occur, and then this emergency call happens at random. Of course, we would assume that you would not receive two emergency calls at the same time per hour. And then finally, you see that these particular events are given within a certain period of time, which is per hour. So if the question asks what are the assumptions, do you need to make to model this with your Poisson distribution? So the answer that you would give is the emergency calls happen singly. So happen singly means that it will happen once per instant. So you will not receive more than one call for at an instance. So then it is also happen independently from each other. And it happens at random. So these three keywords are exactly A, B, and C: random, independence, and singly. So those are the assumptions that you would need to model this particular event as a Poisson distribution. So if let's say you can model this as a Poisson distribution, so what is the probability of 4 calls being received between 11 p.m. at midnight? So between 11 p.m. to midnight would be 1 hour. So you can safely model this as a Poisson distribution. You receive 1 emergency call per hour, so you just write 1. So then Px equals to 4. You want to find the probability of receiving 4 calls. So this will be e to the power of -1, because 1 is your lambda. And then you have 1 to the power of 4 divided by 4 factorial. So when you calculate this, you get 0.0153. So that's how you do a very simple question on Poisson distribution. Of course, you can also adapt it for different intervals. Let me move to a new page. So let's look at how this can be done. It's actually pretty simple. So what you need to do is to use the idea of ratio to calculate the lambda for different interval. So that's all you need to do. So let's look at one example of this. So you have a typist on average making one error for every 200 keyboard strokes. So if you can model this particular event as a Poisson distribution, so find the probability that in a document requiring 400 key strokes, at most one error, and let's say in 2 documents requiring 400 keystrokes with at most one error. So originally you have one error for every 200 keyboard strokes. So originally what you would model is something like this. So this one represents one error per 200 key strokes. So for question A, because you are doing 400 keystrokes, so what you would do is to remodel it by ratio. So this will be 2 errors per 400 keystrokes. So that's how you change your lambda based on ratios. So you want to find the probability that you would get at most one error. So this will be x smaller or equals to 1, which is px equals to 0 plus px equals to 1. So calculate that using your formula. It will be e to the power of minus 2, 2 to the power of 0, 0 power factorial, plus e power minus 2, 2 to the power of 1 divided by 1 factorial. So this is 0.1353 plus 0.2707 So this is 0.406. So now you are typing two documents. Each of the document takes 200 strokes. Sorry, 400 keystrokes. So it means that what you would need is this. So you have 4 errors per 800 keystrokes. Because you type two documents, each has 400. Okay, so you would do the same thing, px smaller or equals to 1, because you are required to find at most one error. So this will be px equals to 0 plus px equals to 1, and this is e to the power of minus 4 power 0 divided by 0 factorial 4 divided by 1 factorial. Sorry. So this would be 0.0183 plus 0.0733, and this is 0.0916. Okay, so that's how you convert between different intervals, just using ratio. The next thing that we are going to look at is to see the Poisson distribution as an approximation to binomial distribution. So Poisson distribution as an approximation to the binomial distribution. So later in the chapter, we are also looking at how to approximate Poisson distribution using normal distribution. So that one is from discrete to continuous probability distribution. So you need to use continuity correction. Over here, this is between two discrete distribution. So the first thing that you need to remember is that this is from a discrete distribution to another discrete distribution. That's why you don't need to use the continuity correction. Okay. Second thing is that you are going to approximate binomial distribution using Poisson distribution. So previously, when we look at approximations, we always have assumptions that you need to fulfill. So the criteria will be n has to be greater than 50 and np has to be less than 5. So now let's look at how we can do it. So on the left side, we have x binomially distributed by n and p. So you want to approximate it using Poisson. Of course, the first condition that you need to satisfy is that if you want this to be valid, so your Ex has to be same as lambda. The variance of x has to be also lambda. So from the left side, your Ex is given by the equation n multiplied with P. So this means that your P will be equals to lambda divided by n. So from the left side, the variance is given by npq, and we know that q is equals to 1 minus p. So this is n multiplied with p then multiply with 1 minus p. Okay, so now you want to test that when you take the limit for n approaches infinity, this particular variance will actually become closer to lambda. So the left side will be equals to the right side, which is the Poisson distribution. So this will be equals to, so this n can be cancelled off, lambda 1 minus lambda divided by n. So you can factor out the lambda, and then just leave with 1 minus lambda divided by n. So as n goes to infinity, the limit will approach 1, and this will be approximately equals to lambda. So which is why when you want to approximate binomial distribution using Poisson distribution, your n has to be large, which is in this case guideline will be greater than 50, but your n multiplied with p has to be small, so that you can still approximate to lambda for your mean and your variance. So that's the reason why. So let's look at some examples. Maybe before that we can talk a little bit about how the formula actually comes. The formula for Poisson distribution, for example. So you know that Poisson distribution is an approximation of binomial distribution when n is very large. So for binomial distribution, usually you are given this particular probability. And this is n factorial divided by r factorial n minus r factorial. So now we are starting to changing the p into lambda divided by n, because we want to see that the limit when n goes to infinity, the binomial distribution will approximate to Poisson distribution. So this is power r. Then you have 1 minus p n minus r. So you want to find this particular limit. So you can do some conversion. So you have lambda to the power of r divided by r factorial. So I'm just moving things around. And then you have the factorial part, which is n factorial divided by n power r and n minus r factorial. Then you have 1 minus lambda divided by n minus r, for example. Okay. So first thing, so maybe I write in red. When you see this particular limit, is e to the power of lambda. So over here we see a very similar term here. So this is minus. So for the limiting case, we will assume that n is very much bigger than r, for example. So we will assume that this thing will go to e to the power of minus lambda when n approaches infinity. So this part on top you have n factorial. So n factorial will be approximately the same order as n to the power of n times. It's not a very accurate approximation, but this will do. So n to the power of r, so n minus r factorial would be approximately equals to n to the power of n minus r. Again, this is not as accurate, but we just want to estimate like what will this number goes to when n is approaching infinity and n is very much bigger than your r. So nr is of course nr. So nr multiplied with n minus r factorial would be just equals to n factorial. N to the power of n. So you can see that this particular term would just approaches 1, because on top you have n to the power of n, at the bottom you have n to the power of n as well. So in the end, this particular limit before this, lambda to the power of r divided by r factorial, there's no n involved, so you can factor this out. So what you are caring about is the term at the back. So if you wonder why n factorial is very close to n to the power of n, you just think of it this way. N factorial is equals to n times n minus 1 all the way until 1. So basically you multiply n more or less n times. That's why it is approximately equals to n to the power of n. So when you evaluate that limit, in the end you would get something like this. So this the first term, the first bracket of the limit goes to 1, the second one will go to e to the power of minus lambda. Okay, so that's how you get this as a Poisson distribution. Therefore, you can say that the limiting case when n is very large for binomial distribution, it approximates to Poisson distribution. Okay? Of course, as I said, this particular evaluation is not as accurate. If you want to really approximate n factorial, you should use the Stirling approximation, which is not covered in this particular syllabus. So let's look at some examples. Let's say you have x is binomially distributed with this parameter. Use a suitable approximation to find P6x10. So the first thing that you need to do is to test your n. N is greater than 50. This is correct. And then n multiplied with p. So this is 2, which is more than 5. This is also correct. Then the third thing is to test your NPQ. NPQ is 1.98. This is approximately the same as NP, which is 2. So this is good. You can use Poisson distribution. So you use Poisson distribution to approximate your binomial distribution. So the mean will be equals to 2. So then you are required to find this particular probability. So you can write down this will be 7. Sorry. X equals to 7. X equals to 8. X equals to 9. So you can factor out e to the power of minus 2. Then just write 2 power 9. Sorry, 2 power 7. 7 factorial. 2 power 8. 8 factorial. 2 power 9. 9 factorial. So multiply everything and then sum everything, you get 0.0045. Those will be your answer. Let's look at another example. For a certain flower, a seed mutation occurs at random with probability 0.0004. A total of 12,000 seeds germinate. So let x be the number of seeds that germinate and carry the mutation. So the first question is justify the use of Poisson distribution as an approximating distribution for x. So what you need to do is to first, obviously n is greater than 50. You don't need to calculate anything. Second thing is to look at n multiplied with p. This is 4.8, which is still less than 5. So the third thing is to C and PQ. So you realize that this is also 4.8, which is approximate, sorry, not approximately, this is equals to n times p. Okay, so wait, I mean, this is technically speaking not 4.8, is 4.79808, but it's very close to 4.8, which is your NP. So these three factors tells you that you can use Poisson distribution to approximate the original binomial distribution. Okay, so use your approximation or approximating distribution to find px smaller or equals to 3. So originally this is binomially distributed. You have 12,000 over here, 0.0004. So now you do some approximation with Poisson distribution. So n multiplied with p is 4.8. So that is your parameter. So px smaller or equals to 3 will be px equals to 0, 1, 2, and 3. So I factor out e to the power of minus 4.8. Then I calculate the rest. So it will be 4.8 power 0 to the 0 factorial, 4.8 to the power of 1 divided by 1 factorial, 4.8 squared divided by 2 factorial, and then 4.8 cubed divided by 3 factorial. So you calculate everything, you get 0.2942. So just a reminder, this is when x equals to 0, this is when x equals to 1, x equals to 2, and x equals to 3. Because you are converting from discrete distribution to discrete distribution, you don't need to do any continuity correction. So the question of part C, calculate px smaller or equals to 3 given that x is greater than 1. So this is a conditional probability. So you want to calculate the probability when x is smaller or equals to 3 provided x is greater than 1. Use the conditional probability formula. So this is x smaller or equals to 3 intersecting px greater than 1 divided by px greater than 1. So this is equivalent to x counting from 1 not including 1 to 3, and then 1 minus px smaller or equals to 1, because for the denominator you want to avoid 1 basically. So what is happening on top? On top you have e to the power of minus 4.8. 4.8 square over 2 factorial because it starts from 2, and then 4.8 cubed divided by 3 factorial. So what is happening at the bottom? The bottom, you have 1 minus e power minus 4.8. Then 4.8 power 0 divided by 0 factorial. 4.8 power 1 divided by 1 factorial. So this gives you 0.2465 divided by 1 minus 0.0477. So finally your answer is 0.258. So that's how you do the approximation of binomial distribution using Poisson distribution. So we stop here for now. Tomorrow we cover the approximation from Poisson to normal distribution, and lastly the hypothesis testing. That's all. Thank you.